Welcome to Lecture 3, Part 2. There will also be a Part 3, but Part 2 will be the beginning of our implementation of the binomial model that we discovered in Part 1 of this Lecture 3. This is Bill Foote. This is Stats 1. And we continue our journey, and it is a journey, maybe even a pilgrimage, to discover intellectual structures inside of data. The simplest data we're using right now is binary data. It's either on or it's off, and we count how many ons, count how many offs. We did this in Lecture 2 as well. Here is the result of Lecture 1's implementation. Recall, we had a bag. You see, we named the range with 4 charms in it. Then this is it. Okay. We created 5 hypotheses to help us answer a question. The question was, please recall. And also, please recall the 5-step process: pose, form hypotheses, pose a question, form an hypothesis, sample observations, get your hands dirty, if you will, count the ways. Then we improved on that counting with the binomial approach. And finally, infer. What can we infer? And right now, Lecture 2 is probably the best inference approach that we have seen. It's a relative approach. We creep up on that approach in Lecture 1 as well here in Lecture 3. So just some guideposts there. The whole course is really about inference. We're also going to look at some descriptions which may defy inference but may feed inference as we go forward. Means, standard deviations, interquartile ranges, mean absolute value, absolute deviations from the mean, quantiles, percentiles. We're going to be doing all of that as we go forward. But right now, let's stick to the script. In Part 2 of Lecture 3, where we are right now, we're going to take what we did in Part 2 of Lecture 1 and reconcile it with the binomial model. In Part 3, I'll give you a little hint. We're going to build this model, a 11-point model. It's literally copying and pasting. It's not anything more than that. But we're going to build a picture. And the reason why I've separated the Part 3 out is because the bulk of Part 3, Lecture 3, is building this picture with 1, 2, 3 curves in it. The gray curve, the gray line is a curve. Primary and secondary y-axis. Dynamic titles. It's going to be done properly in the sense of this is what you would expect a professional Excel application, kind of loosely, to be able to do. Again, named ranges will be used wherever possible. Also, a grid will be established. There's the grid down here, max, and then it's an interpolation grid, very linear. And we're going to use 11 points just to get a little bit more granularity into the picture. We can use 1,001 points, which would be nothing for Excel to calculate, by the way, nothing at all. At least on one sheet. Don't have too many of those open. Going back, ways. So I'm calling this Ways 5 grid. That's the tab. That's the worksheet name in this particular model. We have land, we have water. The question, remember, was what is the proportion of water? What is the most plausible proportion of water might be an emendation of that question on planet Earth. And well, it's not planet Earth, it's a planet beach ball that looks like Earth. Okay. Wish I had that beach ball here. You will see that beach ball eventually when my office finally opens up. Remember, this is being videoed in a pandemic. Okay. I have 5 hypotheses over here. 1, 2, 3, 4, 5. A little bit better than this would be to say equals 0 plus bags. Let me see if I can get this. Oh, no. Okay. It happened because my thumb literally touched my touchpad that's on my Lenovo. Nope, we don't want to see any more updates from you folks. Remind me later. Okay, bags. It's back. Okay. So we have 5 hypotheses. That's hypothesis 1. Oh, no. Minus. See if I'm doing it on the fly. Okay. And I have to subtract 1 from each. So this will be equal to this one So all we're trying to do here is really algorithmize things that are otherwise hard-coded. We don't like to hard-code things in general. And one way to do it is just to take the previous. Let's see if I can do that. There we go. Take the 1 here that was established with bags. Add 1 to it. Okay. And copy this down. And there you go. It's just that we don't like to hard code anything. It's a really bad practice. Not a okay practice. You can do it, but don't hard code anything if you possibly can. And here, I did the same thing. I did not hard code it. I started out with 0 here. And one way to do this is to take this minus 1. There we go, 0. It's no longer hard coded. Everything kind of goes back. And even this 5, I might be able to play with this a little bit. Instead of putting 5 there, I could take whatever's in bags plus 1. You could actually do some algebra to simplify that. Minus bags. Oops. I don't have any bags there. I only have bag. Well, watch what that was. That was good. Let's see. There we go. I mean, otherwise I could just call this 1. Leave bag out of it. Okay. And I algorithmize it. Okay. In other words, I put a formula in it. I don't hard code it. And remember, it's 0 to 4 ways for land, 4 to 0 for water rather, and 4 to 0 for land. And this corresponds to 0 out of 4 possible ways out of bag up there for the proportion, and we parameterized it as well like that. And here's the basic formula down here. And the prior we chose as, well, just anything times 1 is itself. Let's do this a little bit more interestingly, as we did before. And again, we should be able to algorithmize this as well and say equals 1 out of 5 down here. There we go, C11. Make it a formula algorithm. Use it far too frequently. I do anyways. And now it's no longer hard-coded. And that's what we'll eventually call a uniform distribution. I'll use a discrete version of it. Here is our data. 2 blue, 1 land, yes, 2, 1 green. And we can take this in any order. We can be water, water, land, land, water, water. All right, water, land, water. Okay, the combinations, there's only 3 of them. Remember how you do combinations? You have 3 things coming through the door, 1 at a time. There's only 3 ways to do that. But because of the magic of multiplication, we can do any order we want, because 1 times 3 is the same as 3 times 1. I mean, it doesn't matter. Okay, it doesn't matter. That order doesn't matter. What does matter is when we have water and we have 2 of them, we have to look at how many ways water can occur for each of these hypotheses. And we did so, and we multiplied them all through. What did we mean by multiply all through? We multiplied the prior times the way in which water and land, as we observe them, are compatible with each and every single one. Okay, and now look what happened here. Because I multiplied everything by 0.2, 0.2, 0.2, they add up to 4, but it doesn't change the result. It's still plausibility of 0, 0.15, 0.4, 0.45, and 0 again. Now, how do we put binomial into this? Well, we have all of the things we need for a binomial. I'm going to do it the hard way first. I'm going to do a formula. And remember that the binomial formula, let me write it down here. Get this to work. Probability of a binomial formula. Well, let me, instead of writing it out, this is what we did write. There we go. There was the reconciliation that we were beginning to do between the two. Got exactly the same numbers. Here is the formula. The probability of a success, we'll call that a success, X. In the binomial world, the success here is, for our question, water. Given n minus x, so we had n as well as n minus x. N are the number of observations, n equals 3 in our particular case. So 2 water, 1 land is what that would say, given the vertical bars, given an hypothesis, P. And that's equal to the number of ways, which is 3, that complicated factorial formula, P to a power. Well, that's ways to the number of waters, ways to the number of lands. But the proportion of ways we think is 0.25, 0.5, 0.75, 1 out of however many ways there are. And there's a lot of ways that this thing could pan out. And we multiply that times the number of ways proportionately raised to however many lands we have. And that's just one. That's easy to do. And we did all this calculation. Let's put all of this inside of Excel now. Bring that up. And this should be, again, fairly straightforward to do. I'm going to write out. I'm going to make a couple of things up here that'll be a little bit different. We're going to say N and X for our data. Let me move these over here, actually. There we go. This will be N minus X. And now these will correspond to the water and land categories. So we have 3 observations. 2 will be water. And N minus X will be land. Of course, I don't like anything hard-coded. That doesn't have to be. So we will laboriously do it this way. See what I'm doing? I am making borders and making it tidy. Tidiness is important here. It's a good hygiene principle in the construction of any of these spreadsheets, because what we tend to do, again, is we tend to put calculations all over the place and nothing looks visually coalesced. So we're going to change that idea here. Formulas, create, top row, say okay. There we go. Then we go over here to the formula bar. To the left of it, we see there's an N. Oh, there is an X. Those were correctly identified here. So what we're gonna show numerically again is that the Ways plausibilities is going to be the same as the binomial plausibilities. And once we have done that, we will be done with this part of the lecture. So let's build the formula. And we're going to do it 2 ways. We're going to do it the old-fashioned way. Now, this is the probability of X. And I'm going to write this a little differently here. Given N and P, number of observations, is a given here. Okay. And X can change. And if X changes, okay, fine. But it can only be within the realm of possibility. It can't be more than 3 or less than 0, right? Okay, we should probably put that into this system. In fact, the number of water here is equals X now. And the number of land here is equal to whatever N minus X is, which should be equal to N minus X up here. And now I have less thing hard-coded, have the right thing hard-coded, which is the data. The only thing that should be hard-coded here. I'm not going to make that n minus x. No, not going to do. That's just a label there. And labels tend also not to be hard coded in these. We would put labels somewhere else and store them in a worksheet so that we can maintain the labels and then float those labels across user worksheets. Okay, that's more than what we need to do right now. Not much more. So the first one here is we're going to calculate equals the number of ways. And this will be with none of that. Okay, factorial. Notice there is a factorial item there. And if we do that, this will be factorial n. That's an enumerator divided by open parentheses factorial x. Some reason or other that's happening. A lot of interesting things are happening on my computer. That's not a good thing to have interesting things happening on your computer. Factorial x times factorial n minus x. Again, nothing up our sleeves. And we've got an extra. I don't need that. I don't need that. Yes, I want to make that into a parentheses. Yes, good. So it intelligently saw that. Okay. So that's something that's literally going to be hard coded no matter what happens all the way through here, because hard coded in the formula, because I made absolute references to n and x all the way through. This formula will work anywhere in this spreadsheet. So I'm going to multiply that times whatever p is in this column. There we go. And here's one of them. And I'm going to raise this to the x power. Notice how well this follows. It's the caret is the raising of the power times open parentheses 1 minus p, and that p again is over here a value in a cell. Okay. This too is raised to the power of, remember, we want this to work everywhere. Let me copy it. N minus x. How clever is this? But make sure you put that in parentheses. So let's see what this comes up with. There we go. Should come up with 0. Now let's further copy it down. And don't those look familiar? Check your notes. You can check it over here too. There we go. Same numbers. 14, 1, 37, 5, 4, 2, 2. The answer is 42. And there we go. And that works perfectly. So let's shift down arrow. Okay, make sure I fire up that particular cell. Shift down arrow, format over here in home, make it number, done. Okay, we're not done yet we need to take whatever this is, the probability of data given assumptions about the data, conditions on the data, namely hypotheses, and that's formally correct. And take this prior is really PR of an hypothesis, and make that a small h, because that's what we've been doing all along. The probability of seeing hypothesis 1, 2, 3, 4, or 5. We're going to play a little game with that soon. So one way I could do that is take whatever is written here, concatenate it, that's the and sign, with whatever is written here. There we go. How clever was that, right? Not being clever and just using Excel. Not having to write this thing out all the time and probably do it wrong. So I take this number, that's what the formula is saying, times that number, the 0.20. Copy that down, format it. There we go. Might want to expand it a little so that it looks a little bit like what we had again. There we go. We're in the Bronx, home of drag racing. 0.0282, 0.075, 0.0844. We know that's going to add up to a year, 1876. Interesting year. There we go. And we can add it up, call this a sum. In other iterations of this, I'm putting the sum up here. Oh, 1875, excuse me. Okay, so rounding, don't let it worry you, but make sure you got your numbers as well contrived as you can, okay? I'm not gonna let it worry me too much. It's within the ballpark, huh? Let's put some, there we go, and let's make this a formula. Top row. And let's make this a different name. Okay, let's call it sum, because it said it's already somewhere else, and I might want to use that somewhere else. Underscore is often used here for, let's put in a 5 grid. Okay, so that we have some identification here that's unique. And let's put it like this. Watch how it always goes. Same thing. There we go. And center it. So again, it's easier to read. Okay, cool. And finally, we get PR of H given data. And there's a involved formula for that, but I'm avoiding that for a while. Okay, I want you to please focus on what's going on right here. And I'm just going to put an underline here, put a line under it. Okay, bottom line. Very cool. And what are we doing? We're taking this probability of seeing data in the presence of an hypothesis at the same time as we pose that hypothesis. That's the probability of H. Both and is a multiplication, just like we did with the ways, both and. So we take this number and divide it by to get the relative strength. Oh, it's always going to be 0. And there we go. We get exactly the same numbers. And make these numbers exactly the same numbers. And I said that would be it. I lied. There will be one more thing. These are relative frequencies, where this is the proportional frequency. It's the relative frequency in a sense, but we need these relative to each one of these. So we're going to build this as billet as a relative frequency. I want to see their accumulation. Okay. And that's the notion of like area under a curve, calculus notion, and we will go into that when we hit part 3. But let's just calculate it here. It's going to be equal to, first one is going to be equal to 0, plausibility. And as we move from hypothesis 1 to hypothesis 2, this one will be equal to whatever we had here. Remember, this is an accumulation, plus the increment, 0.15. And we can build this all the way up, and it hits 1 pretty quickly. Should hit 1 right here, because this is 0 increment. And this is the notion of the increments are literally derivatives, numerical. This is literally an integration from hypothesis 1 to hypothesis 2, hypothesis 1 to hypothesis 3, hypothesis 1 all the way up to hypothesis 4, 100%. We can also figure out from hypothesis 1 to hypothesis 4. That's just 1 minus 0.15. That's the area under the curve, the area under this digitized curve. Okay, keep that in mind as we move forward. And with that, I close down lecture 3, part 2. Stay tuned for part 3. Again, thank you very much for your kind attention. And there we go, for your kind attention. And we'll close this down. Take care.